So, you decided to find a word in a dictionary. Imagine you're searching for a long, complicated word in a dictionary, one that anyone can barely pronounce. Numino-ultramicroscopic silica... Okay, you got it. Let's get back to the problem. You open the dictionary and start flipping through each page, looking at every entry. This process is called a linear search in computer science. Linear search is straightforward, but what if the word you're looking for is near the end of the dictionary? In that case, you'll have to flip through almost every page to find it. This may seem pretty slow, right? But first of all, what do we mean by slow here? Why is it slow? Who decides this? Slowness is relative. For something slow, there must be something fast. So how can we measure the speed of searching through a dictionary in computer science? We use the concept of time complexity, indicated by the symbol O, like this: O of 1, O of n, O of n times m, O of n squared. What's the time complexity of a linear search in a dictionary? If there are n words in the dictionary, it's O of n. So, if there are 10 words, you might have to check all 10 in the worst case. If there are 1 million words, you might have to check the whole million. Is this slow or fast? To understand this, we must compare it with another method of finding the word. After flipping through hundreds of pages, you realize this is madness and close the book. There must be a faster way. Yes, actually, if you open the book right in the middle, you'll have two equal or almost equal parts. The word you need is in one of the halves, therefore you can easily get rid of the other part. This process can go on and on, narrowing down the range. This technique is called binary search. Is binary search slower or faster than linear search? Let's see. If there are 1 million words in the dictionary, only 500,000 words will remain after the first step. After the second step, 250,000 words will remain. This process continues until you find the word. So, how many steps will it take to reach that one word? The answer is 20. But how do we know this? At each step, we divide the total number by 2, right? Let's find out how many times we can divide 1 million by 2 to get around 1. The easiest way is to calculate which power of 2 gives us this result. A little magic of math. 2 raised to the power of x equals 1 million. And taking logarithms on both sides, we find that x equals the logarithm base 2 of 1 million, which is roughly 20. So, to find the word, you need to perform about 20 searches for 1 million words. Now you can see why I said linear search is slow. It's just terrible compared to binary search. The time complexity of binary search is O of logarithm n. The 2 is skipped in the notation for simplicity. To understand why it happens, you can read more in the article in the description. And now, what if, instead of splitting the dictionary in half, we separate it into 3 equal parts? In this case, you will be able to throw away 2 out of the 3 parts of the book. This method is called ternary search. You may think, which one is better, binary or ternary search? While you're writing your answer in the comments, let me tell you. It depends. In binary search, you make decisions based on one word, finishing in 20 steps. In a ternary search, you finish in 13 steps but make decisions based on 2 words, totaling 26 searches. So, binary search wins in this case. However, there are scenarios where a ternary search is better. From this, we can conclude that splitting into 4 parts is also not a good idea, as well as into 5, 6, 7, but not into 26. Yeah, you heard me, but let's make a quick setup. Write down the positions of the first words of each letter in the dictionary. Note that these intervals are not equal in length. Now, if you're searching for
Numino-ultramicroscopic silicovolcanoconiosis,
you know it falls between the first words of P and Q. This way, you can discard 25 out of 26 letters. That's huge, but let's not stop here. Do the same for the second letter in the current range. Some combinations will be impossible, so we can skip those. And what we have now? Now, you found out that
Numino-ultramicroscopic silicovolcanoconiosis
is between P, N, and P, O. With this step, we again took a single interval out of 14. Let's move forward and do this process for every valid letter prefix combination. This process is called creating a trie or prefix tree. In general, to find the word
Pneumono-ultramicroscopic silicovolcanoconiosis,
you perform the following steps. Find the starting word for P, then P-N, then P-N-E, then P-N-E-U, and so on, until you find the exact word in 45 steps. The good thing is that writing down the positions is a one-time job. Once done, you can reuse the mapping to find any word. But why is this method fast? We took 45 steps, whereas binary search needs only 20. The thing is, the number of steps is equal to the number of letters in the word. In our case, we are searching for the longest word in English, an extreme case where binary search performs better. But on average, the length of a word in English is about 5, so you will find the average word in 5 steps. That's a significant improvement. In terms of time complexity, we write O of L, where L is the word's length. This is a good example of an algorithm, which on average is better than binary search, but in the worst case, binary wins. Also, trie can handle any number of words, so no matter how many of them you have in the dictionary, you will always find your word in 45 steps. This means that if there are more than 2 to the power of 46 words in the dictionary, a prefix tree will outperform binary search even in the worst case. Do we have anything else? Sure! There's another technique called hashing that can achieve similar results as in trie, but that's a big topic and it belongs to another video. Thank you for sticking with me to this point. Please subscribe, drop a like, and comment if you like this new format. Your feedback is really important to me. Thanks again and see you in the next video.